will go up to, oh, thank you. Yeah, you're good, Caleb. Yeah, if anybody else has their test corrections and you want to submit them, just go ahead and park them up here, and that's fine. I'll try and get them graded by Monday, no guarantees. I'll for sure have them graded by Wednesday. Okay, thanks. The other day, we were talking about the idea of modeling movement where things are directly proportional. Directly proportional means as one gets bigger, so does the other. As one gets smaller, so does the other. Okay? One example of that, where the equation would look like y, the value that's coming out, is equal to some number that you put in raised to a power times some other number. Now there's a whole lot of some number, other number, a whole lot of stuff there that is pretty vague, Chuck. What's going on? Well, let's take a look at a situation that will help make this look a little more reasonable. Okay, we were talking about the pendulum problem the other day. I'm going to back up and go through it just to warm up your brain, just in case you've forgotten or some of it slipped away. Okay? The time that's required for a pendulum to make one swing. So it goes from the left side, swings all the way right, swings all the way left. That's one swing or one period of the pendulum. And we talked the other day that controls how fast or how slowly the clock moves. If the clock is running fast, you want to take and move the weight on the pendulum one direction or the other. Ah, yes, that's the question. Okay, one of these days you get a really nice job. You've got a gorgeous house with a big spiral staircase coming down into a landing where the front door and stuff is. And there's this gorgeous grandfather clock there, and the way you adjust if those things are running fast is by moving the weight on the pendulum up and down. If the clock is running slow, how do you make the clock run faster? I'm not going to touch it, Chuck. It looks expensive. It's your clock. To make the clock run faster, you take the weight and you move it up. To make it run slower, you move the weight down. As you move the weight down, the weight has more leverage, so it's going to swing further out. And as it's swinging further out, it takes it more time to travel over and back because it's traveling more distance. If you move the weight up, now it's swinging faster, and it takes less time to go over and back. Okay? So the way that a pendulum works is just like that. The question is, okay, so how far do I have to move the weight? Well, you just kind of move it a little bit and see what happens, and over a period of a week or two, hopefully get it fixed. Okay? Okay, we're given some information here. A 2-foot pendulum takes a minute 0.57 seconds to swing over and back. Now there's some information. Okay? The question is, first, compute a constant to fill in the equation, and then figure out what you would do with a 5-foot pendulum. Now, if it is directly proportional, the length is proportional to the square of the period. Say what? The length is proportional means you got to adjust it by multiplying by some number, to the period squared. The length is proportional to the period squared. So you start out with that formula. The first thing we need to do is to figure out a value for k. Well, we were told the length is 2. We were told the amount of time that it takes to complete one swing over and back is 1.57 seconds. And we need to figure out what that value is that you put in front there. Do you know how to solve for that? Are you okay with that? Is that pretty straightforward? What you want to do is you want to divide by this 1.57 squared to get those to cancel. Well, we'll divide by the 1.57 squared, which will then give us the k is going to be about 0.81. Now that's just a number that's in there. It's a coefficient. Okay, it's not how long it takes it to swing. It's not how long the pendulum is. It's just an adjustment that's in there to get the equation working correctly for that particular pendulum. Okay, if you take and you move the weight, so here's the arm of the pendulum, and the weight was up here at 2 feet. If you slide it down here to 5 feet, okay, how is that going to affect the amount of time it takes it to swing over and back? Well, what we can do is we can use this exact same formula as before. We know that the length is now 5, and now we know that k is 0.81, and we're going to have t squared. This time we have to solve for t, because the question is how much time does it take? Does that make sense to everybody? So what I'm going to do is I'm going to divide by the 0.81. Those will cancel. Divide over here by the 0.81. And what we then have is t squared equals 5 divided by 0.81. Well, that's something you can figure out on your calculator. Divided by 0.81 equals, wow, 6.1728, something like that. But that is not the answer. Why isn't that the answer? That's right. Yeah, this is t squared, isn't it? And we want to know what t is, so we're going to have to take the square root of that. Okay, so when I do the square root of that number, it gives us 2.48 seconds. So what this is telling us is if you've got a grandfather clock with a long arm on the pendulum, and the weight's up here at 2 foot, so you've got 2 feet down from where it's swinging from, it'll take 1.57 seconds to go over and back. If you take that same weight and slide it all the way down to the bottom, so now it's a 5-foot length, and you let it swing over and back, it's now going to take, how long? 2.48 seconds for each swing. Notice, we more than doubled the length, didn't we, of the pendulum? Did it double the time of the period for one swing? It didn't double it. It doesn't double it. It went from 1.57 to 2.48. You see that it's not a doubling? So you got to be careful when you get into this stuff where it's proportional. It's not always going to work the way that it might first guess it would work. Well, gosh, if I move it from 2 feet to 4 feet, it'll take twice as long. No, it won't take twice as long. Okay, so with your nice house and the grandfather clock in the front entryway, you want some nice lighting on the outside. Lighting on the house, lighting up into the trees, some cool stuff. I don't know if you've seen houses that are really nicely lit at night. They look pretty cool. It makes a difference. Okay? Not like us where you just turn on the front porch light and there's the lighting. Doesn't make a whole lot of difference. Okay? When you're dealing with lighting, when you're dealing with sound, okay, when you're dealing with transmission of energy like that, The further away you get, the more or the less of the original sound do you get? Less. With light, it's the same way. The further away you get, the less light there is in any one little unit of space. So as the distance increases, the intensity of the light or the sound decreases. You've all experienced that. Okay? That's called being inversely proportional. It means as the one thing gets bigger, the other thing gets smaller. An equation like that looks like you still have your k, but the x is in the denominator. Now you've got to be careful because sometimes it'll be written like this: k x to the negative n. What's the negative mean? The negative means that you want to put that exponent, or not the exponent, that variable in the denominator. So that's another way to write it. So be careful. It's easy when you're looking at the equation to overlook that negative sign. Okay. All right, so what's an example of inversely proportional? Well, as I mentioned, lighting. The further away you get, the dimmer the light gets. You all know that. Which is a good thing in some ways, because if we got the full intensity of the sun's lighting, we'd all be roasted to a crisp and nothing flat. Okay? But by being 93 million miles away, it's a little bit more subdued. Okay. We're told that at a distance of 3 meters, how long is 3 meters anyway? Okay, along in that range. A meter is about the same as a yard. Okay, so it's a little bit under 15 feet. Okay, had the guts to guess at it, take a shot at it. It's about 9 feet. It's a little bit more than 9 feet. So this isn't a big, long distance. So you've got a 100-watt light bulb, produces an intensity of 0.8 watts per square meter at a distance of 3 meters. The 0.8 watts is a measure of amount of energy reaching that surface. Okay. First, compute the constant of proportionality and determine the intensity at 2 meters. Hey, should the intensity be more or less than that 0.88 watts per square meter? At 2 meters, should it be more or less than the 0.88? Hearing some less. More. Originally, we were at 3 meters, right? Is 2 meters closer or further away? Closer, and as you get closer, should the light intensity become brighter? Yeah, you're getting more of the light. So it should be more than this 0.88. How much more? Well, we're not sure just yet, but we know it's going to be bigger than 0.88. Okay? So let's take a look at how this works. Inversely proportioned to the square of the distance. Say a what? Okay? The length, proportion, inverse means it goes in the denominator to the square of the distance is d squared. Actually, I put L, it should be intensity. Should be an I. Thinking about the length between them. Okay? The distance is the length between them. When you are given the original set of information, it allows you to compute what K equals. You need some starting information to get what K equals. The intensity is going to be 0.88 equals K over whatever the distance is. This is 3 meters squared. Now the thing to be careful of here is this is working in terms of meters, isn't it? So if they give you something in terms of feet or whatever, you got to change everything. Okay, so we have 0.88 equals k over 3 squared. How would you find k? Yeah, multiply both sides by 9. Does that make sense? So you're going to have the 0.88 times 9 equals k. So this is going to give us the k is equal to 7.92. This value will allow us to write our equation as the intensity is 7.92 divided by the distance squared. Okay, so once you have your constant, you're set to go. What was the distance we were going to work with on this one? 2 meters. So the intensity here is going to be the 7.92 divided by the 2 squared. And when you work that out, it works out to be 1.98 watts per square meter. Is that number bigger than what we had at 3 meters? Yeah. Which is what was expected. The closer you get, the brighter or more intense the light appears. Whole point of that, get you used to working with something where the two variables are inversely related. Okay? Where one thing goes up, the other goes down. Okay. What we're going to take a look at now is inequalities. And I'll be straightforward with you. Inequalities is basically where we live. It's where you live. Okay. When they've got a capacity for this room and they say 42 people, does that mean that we have to have 42 people in this room before we can have class? No, it means 42 people or less. So the capacity of this room is less than or equal to 42. Okay. There's a bridge. Kind of in front of our farm, just a little bit down from in front of our farm. They replaced it here last year, thankfully. But it used to have a sign that said 3-ton limit. Now when it says 3-ton limit, what does that tell you about the bridge as far as the amount of weight you can put over it? No more than 3 tons. So the limit in that case is less than or equal to 3 tons. So if the car weighs a ton, you're good. Okay? My truck, empty, without anybody in it, weighs 3 tons. It's a diesel. It's a big truck. That means that if we were going to honor that sign about that bridge, anytime we wanted to drive across it, I guess I'd have to stop short of the bridge, get out, and with my foot just kind of go, oof, and try and push the truck across the bridge without me on it. Because with me in the truck now weighs more than 3 tons, doesn't it? Oh, yeah. I didn't do that. We drive it across there trusting that, okay, it says 3 tons, but I bet you they built it for more. Okay? The neighbors and I ran lots of loads over that bridge that were 5, 6, 7 tons. Now, here's something interesting for you. When they hung the sign on that bridge and it said 3 tons, did the engineers really expect it to break a little over 3 tons? Or do they underrate the capacity of the bridge? They underrate it because some idiot with their grain truck's going to go over with 5 tons on it. We did that all the time. So the only way to get it up to harvest land, to the silos. Okay? And we were just trusting that they over or underrated the bridge. They said 3 tons. I don't really know how much you could hold. I've put at least 6 tons on it. Guess I shouldn't be telling you this. It's a new bridge now. It's a good bridge. Okay? But what I want you to realize out of this is that inequalities are what life is about. Hey, next Saturday, a week from tomorrow, Daniel's hockey team's coming over for lunch. Pre-game lunch. Guys will be there. The coaches will be there. We're going to make chili and burgers and all kinds of stuff, and they'll just have a big feeding frenzy. There are about 18 guys on the team and 3 coaches. Should I plan for, let's see, 18 plus 3 is 21. Should I plan for 21 people, more than 21 people, or less than 21 people? More than 21. Why more than 21? Just think, yeah. Okay, these guys are 16 to 18 years old. Ladies, if you don't have a brother around, a 16 to 18-year-old can do amazing things to a refrigerator to make it empty. I'm planning for way more than 21 people, like maybe 30. Because the last thing you want to do is run out of food, right? So this is another one of those situations where it's an inequality. I'm not planning for exactly 21, and as the last bean comes out of the scoop in the pot and dumps into somebody's bowl, yeah, no thanks, I don't want any more. We don't want to have that. We don't want it at exactly down to the last bean. We want to have stuff left over. There's an example where it's an inequality. We want the food greater than 21 people. Make sense? So realize that with these inequalities, sometimes people say, well, this is stupid. Where do I ever use this? Inequalities is where you always work. How about you walk into Kroger's, you got 20 bucks in your pocket. That'd make an interesting song. Got $20 in my pocket. Okay? You got 20 bucks in your pocket. You walk in. The only thing you're concerned about with regard to the stuff going into your cart is that it rings up at $20 exactly? Less. As long as it's less than or right at 20 bucks, you're fine. Anything over 20 bucks and you're that embarrassing person, could you take this off of my... No, put that back on. How about take this... Okay, there we go. There we got $20. You know, everybody's behind you. Really? Okay? So realize that these things really do come into play. When you're doing inequalities with polynomials, what you're going to wind up doing is a couple of things. Okay? Let's say that we have something like this. We want x cubed is greater than 2x squared. Now, on this is just flat out something to practice. We've not put it in the context of some problem where there's all kinds of words and stuff like that around. Because we want to just keep it down to the stripped down basics and all that's needed and nothing else. In this case, we need to know where x cubed is greater than 2x squared. We could do something like you take a snowball. I guess they're all melting now. Take a snowball and you throw it up in the air, and you want to know when is that snowball going to be more than 20 feet off the ground. That would be an equation like this. Negative 16t squared plus, let's say, 45t plus 5 greater than or equal to, let's say, 20 feet. That would be a more realistic polynomial to work with, but who wants to work with that one right now? Yeah, maybe we'll save that for later. So I want you to see that there are other polynomials coming to a classroom near you soon. Okay? But we're starting out with something a little bit less involved. I'm going to start out with this one that we've got there. We're going to rewrite it as this x cubed minus 2x squared greater than 0. Now, the first thing we want to do is to get a number line going. And on this number line, we're going to put some specific x values that are important to this problem. To figure out what those x values are, we're going to swap the greater than for an equals. And we're going to solve this equation. You can factor out an x squared, and you have x squared times x minus 2 equals 0. Now, if you've kind of tuned out, catch this. Do not divide by x squared. It's tempting. It'll still give you the x minus 2, but the x squared's gone now, isn't it? When we solve this equation it's showing here, we get x equals 0 or 2. Those are the solutions for this one. If we would have divided by x squared, we would just have x minus 2 equals 0, which would give us x equals 2. And now do we have the same solutions that we would have had before? You see it? We've lost one of them, haven't we? Anytime you divide by x, you lose x equals 0 as a solution. So don't divide by the x to get rid of it. Okay, so what am I going to do with these two numbers? Well, up here on this number line, I'm going to put 0, and I'm going to put 2. And now I'm going to do a test. This is only a test. I'm going to check and see what happens over in this area. What are some x values over in that far left end of that number line? Yeah, things like -1, -3. Is any number better than another number on that side? No, they're all in the same area. They're all equally valuable. I'm just going to pick x equals -1. Myron mentioned that. Okay? So we'll run with x equals -1. Now, what I want to know is if I plug x equals -1 in, do I get a positive or a negative value? Well, let's see. That's going to be a -1 squared times -1 minus 2. All I want to know is it positive or negative? The -1 squared is positive. -1 minus 2 is negative. And when you multiply a positive times a negative, what do you get? You get a negative. Aha. That tells me that if I pick any number over on this left end, the result I'm going to get back is negative. Okay, in this next interval from 0 to 2, what's a nice number there to work with? 1. So let's use x equals 1. Okay, so if I plug a positive 1 in here, the 1 squared is going to be positive. The 1 minus 2 is going to be what? Negative. So that means anything on this interval is going to be what? It's going to be negative as well. Notice, notice, notice. Do these things alternate back and forth, negative, positive, negative, positive? No, you've got to check it. Sometimes it will, sometimes it won't. So you've always got to check it. Don't just assume. On the rightmost interval, to the right of 2, what's the next value there that would work? 3. So if we take 3 and we plug it in, let's see what we get here. We're going to have 3 squared times 3 minus 2. Well, the 3 squared is positive. The 3 minus 2 is positive. A positive times a positive is a positive. Okay, now, here is where we get the payoff. We want to know where this inequality is going to be greater than 0. Greater than 0 means positive, doesn't it? What values of x will give us a positive result? Okay, greater than 2. If we plug 2 itself in, it's going to zero out. Really? Yeah. Here, let's plug in 2 down here in the lower right. Well, let's see. We're going to have 2 squared is 4 times, what's 2 minus 2? 0. Oops, 4 times 0 is 0. Now be careful. Is 0 bigger than 0? No, it's equal to 0, but it's not bigger than 0. So 2 does not work here because the inequality just says greater than. If it would have said greater than or equal to, would it have worked? Yep. That's right, because it could be equal to or greater than 0. All right, so up here on this number line, we're going to put an open dot. We're going to go to the right. What this tells us is the solution is x belongs to infinity. The 2 has a parentheses, not a bracket. The squared one, not the squared one. The squared one means you can include 2. This one you don't want to include 2 on. Okay? Does that make sense? Anything higher than 2 will work. That's it. Anything bigger than 2 will work. Does that make sense to everybody? Another way to write this is x is greater than 2. All right. There we go. Yeah, we've got all this done. That whole routine's done. There. Whew. Zoom through a bunch of them. Okay. Rational inequalities. What on earth does that mean? Rational means you got a fraction. A rational number is something like 2/3. Okay? So you got a fraction going on here. All right. Well, let's take a look at this. A ticket booth attendant can wait on 30 customers per hour. So this might be something like Kings Island or whatever, where you got to come up and they're going to take your picture and then make your picture or make your card to get in. Okay? I suspect some of you have done that when you're walking up to the entrance ramp. You go to the left and there's that separate little building and there's a line and you wait your turn and they move you through as fast as they can, but it takes a little time. Okay? So maybe something like that. Can take care of 30 customers an hour. To keep the wait line reasonable, they don't want to have more than 8 customers on average in line. Wow, that'd be nice if Kings Island had wait lines of 8 customers or less, wouldn't it? Okay, dream on. Solve the inequality to determine the rates x at which customers can arrive before a second attendant is needed. Note that the x values are limited to 0 to 30. Now, let's talk about that first. How do you know that x is between 0 and 30? Well, what does x represent? The rate at which customers are arriving. X is how many customers are walking up at a time. If it's more than 30 walking up at a time, do you need a second attendant? Yeah. Why can't it be negative? You can't have negative customers. Well, I guess you can. They start grumbling about the line and leave. That'd be a negative customer in a variety of ways. But we're keeping it between 0 and 30. Okay, here's the equation that we're given. You're the manager. Okay. At what rate can customers walk up before you've got to look at hiring a second person and open up a second window for tickets? Opening up a second window is expensive because now you've got to have a whole second set of equipment, don't you? Whatever's at the first window, computers, etc., has to also be at the second window. Plus, you got to hire a second person. Okay? So it gets expensive as soon as you hit 2, and you want to keep it at 1 as long as possible without customers becoming negative. It's a delicate balance. Does any place around here do anything like that? Does any place around here worry about stuff like that? Yeah, maybe Kroger's. Okay. Have you ever heard the ads? All lines open 4 to 6 p.m. daily. Why do they have a bunch of lines open between 4 and 6 p.m. Monday through Friday? What happens between 4 and 6 p.m. Monday through Friday? People are leaving work and going home, and on the way home they need to pick up food. If Kroger promises you'll always be no more than the second or third person in line, are you more interested in going in there? Because remember, going in, you're already hangry, right? Angry and hungry. Hangry. So you don't want to now find your 47th in line as well. That's why they've got all lanes open from 4 to 6 p.m. They're concerned about this very same thing. Okay, X is the arrival rate. If we want to keep the number of customers to 8 or less in line, what does the arrival rate need to look like? Well, there are a couple ways of solving this. One way is to graph it. And if you have one of those nifty cool graphing calculators, you can put in y equals 8 and then put in y equals the x squared divided by, and you get the routine. What you want to solve for is the x value of where the two lines intersect. This is the x value of where they intersect. We've talked about the fact that you can solve for that. And when you do, you get x equals 26.969. Now be careful, x represents what? Customers. Can we use a decimal? No. If you've got 0.7 of a customer, you've got a problem. It's time to call EMS. Okay, or maybe too late to call EMS. So this is really going to be x equals what? 27 customers. Okay, so what does that mean? 27 customers. And here's where the tricky part really comes in math. Is you've got a number, how do you explain it to somebody else? How do you explain what x equals 27? Okay, let's move on to the next problem. Are you feeling a little like you've been gypped? Because you're really not completely comfortable yet with what x equals 27 is telling you to do, are you? Okay? If the arrival rate is more than 27 customers an hour, you got to open up a second booth. If there are more than 27 people an hour coming up to that line, you've got to have a second line. Otherwise, you're going to have too many people in line, and the wait time is going to be too long, and you're going to have hangry customers. Okay? That's what the 27 tells you. What's the maximum arrival? 27 an hour. Does that make more sense? Are there other ways to solve this problem? Gosh, Chuck, what if I don't have a graphing calculator? Now what do I do? Well, you can rewrite this as x squared over 900 minus 30x minus 8 less than or equal to 0. You could combine those. How could you combine those two things? You need to get a common denominator, put them together, and solve for this. Where is it less than 0? Now, how do you figure that out? Well, let's go after another problem that might be a little bit easier to work with. Let's say we have something like this one. We need to know, in a different scenario, 1 over x less than or equal to 2 over x plus 1. It doesn't matter which side you move things to. Just make sure you keep the inequality pointing in whatever direction it's pointing in. The only reason that you flip an inequality is if you do what? Multiply or divide by a negative. Way to go, Jasmine. Okay, so unless we're multiplying or dividing by a negative, we're leaving it alone. So I'm going to rewrite this as 1 over x, subtract 2 over x plus 1, less than or equal to 0. To get a common denominator, multiply the first one by the x plus 1 over x plus 1, multiply the second one by x over x, and you're going to have x plus 1 over x times x plus 1 minus 2x over x times x plus 1 less than or equal to 0. Now be careful. In the first term, there's an x plus 1. Should I cancel those? We can cancel them, should I? No, because if you do, it'll get rid of your common denominator. Oh, yeah, I guess not. Okay, so what we're going to have is we're going to have x times x plus 1 less than or equal to 0. In the numerator, we have an x minus 2x. So that's going to be a minus x plus the 1. Now, here's where the tricky part comes in. Just like before, we're going to put down a number line. And there are two places that we want to note on this number line. The first place we want to note is where does the numerator equal 0? The second place we want to note is where does the denominator equal 0? Where does the numerator equal 0 on this? What value of x will cause the numerator to be 0? Do you buy that it's x equals 1? Okay, so we can put a 1 down here. Now, is it legal to have a 0 in the numerator? Well, yeah, that'll make the whole thing 0, and here it says less than or equal to 0. Oh, okay, so 1 is okay. I'm going to use a solid dot because that's a legal point to use. Now let's look at the denominator. What is one value where the x will cause the denominator to equal 0? 0. Okay, so we'll put 0 down on this number line. Are we allowed to actually let x equal 0? No, because that'll give us a 0 in the denominator, won't it? Which is a problem. So I'll use an open dot there, kind of like a pothole that you would drive around, avoid, not hit. You get the idea. We have this x plus 1. What value of x will cause that to be 0? Negative 1. So I'm going to put a negative 1, and once again I'm going to use an open dot because we're not really allowed to be there, are we? You know what we do next? You pick a number from over in this area. Something like x equals a negative 2. And you plug it into your equation and determine, do you get a positive or a negative value out? Let's see, if we put in a negative 2, it's going to be a positive over a positive, so it looks like that's going to be a positive. So all the numbers on that interval look like they're going to be a positive. Can we use those numbers as part of our solution? No, because we want results that are what? Negative. So that would say that anything in this interval doesn't work. Pick a number between negative 1 and 0, something like negative 1/2. Pick a number between 0 and 1, something like a positive a half. Pick a number over here, something like 2. And see if it comes out positive or negative, and then only pick out the intervals where it's a negative value. Does that make sense? Okay, and actually that covers a whole lot of these and finishes off section 4.7. How about that? Folks, I hope you have a terrific weekend. I look forward to seeing you all on Monday.